Hello, and welcome to our 2015 update. This past year marked the 25th anniversary of the Hubble Space Telescope. We're going to see caverns carved out of dust by new stars. We're going to get a look at the Veil Nebula moving. We'll see it expand. We'll see through the Eagle Nebula. We'll take a very close look at the Andromeda galaxy. We'll see a galaxy on the edge of the local void. Also in 2015, CERN reopened the Large Hadron Collider after a 2-year closure to upgrade the power to almost twice what it was when they found the Higgs boson. At these levels, it might be able to find dark matter. And Hubble discovered a supernova, predicted it, and found it due to gravitational lensing around dark matter. So with two key 2015 updates, I thought it'd be appropriate to dig deeper into just what dark matter is. So we'll conclude this update with a deep look at dark matter. But first, let's take a look at the updates from inside the Milky Way. Here we are zooming into the great Orion molecular cloud. As we enter the cloud, we see the jets from a central star that is hidden by gas and dust. The jets collide with the surrounding gas and dust and clear vast spaces, like a stream of water plowing into a hill of sand. The Hubble Space Telescope is entering its 25th year in operation. Here it imaged 3 sections of the beautiful Veil Nebula in 1997. We saw those in our segment on star clusters and supernova. In 2015, Hubble took another look, overlaying new images with the old. This allows scientists to study how far the nebula has expanded since it was photographed over 18 years ago. Despite the nebula's complexity and distance from us, the movement of some of the delicate structures is clearly visible, particularly the faint red hydrogen filaments. Hubble has also revisited the famous Eagle Nebula, capturing the multicolored glow of gas clouds and wispy treadmills of dark cosmic dust. With these new images come better contrast and clearer views of the region. In addition to this new visible light image, Hubble has also produced an infrared image. Infrared penetrates much of the obscuring dust and gas and unveils newborn stars hidden in the visible light view. Here we are zooming into the Milky Way's center, 26,000 light-years away. This is a small section of Hubble's view of the dense collection of stars crammed together in the galactic bulge. Gaia is the mission to record information about 1 billion stars. It has now accumulated 340 billion positional measurements, 68 billion brightness data points, and 6.7 billion spectra. This image, based on housekeeping data from Gaia, portrays the outline of our galaxy. It was obtained by plotting the total number of stars crossing Gaia's focal plane per second. This is a measure of the density of stars in the region that is being scanned. In 2015, the Hubble Space Telescope captured the sharpest and most detailed image ever taken of the galaxy. It shows over 100 million stars and thousands of star clusters embedded in a section of the galaxy's disk, stretching across over 48,000 light-years. It traces the galaxy from its central bulge on the left, where stars are densely packed together, across lanes of stars and dust, to the sparser outskirts of its outer disk on the right. Zooming into the boxed field, we see some foreground Milky Way stars in the line of sight to Andromeda, and a couple of distant spiral galaxies shining through Andromeda's disk. The large group of blue stars in the galaxy indicates star-forming regions in the spiral arms, while the dark silhouettes of obscured regions trace out complex dust structures. Underlying the entire galaxy is a smooth distribution of cooler red stars that trace Andromeda's evolution over billions of years. A large number of star clusters can be seen in this analysis of Andromeda. This 150 light-years across view of AP14 and others like it are helping astronomers interpret the light from more distant galaxies that have similar structure. Astronomers have previously noted that the Milky Way sits in a large, flat array of galaxies called the local sheet. This sheet of galaxies bounds a void called the local void. The void's size is not known, but it is at least 150 million light-years wide and 230 million light-years long. Its center is approximately 75 million light-years from us. Hubble has taken a beautiful picture of NGC 6503, a lonely galaxy on the edge of this void. It spans some 30,000 light-years. In this image, bright red patches of gas can be seen scattered through its swirling spiral arms, mixed with bright blue regions that contain newly forming stars, with dark brown dust lanes snaking across the galaxy's bright arms and center. Hanny's Voorwerp is one of the strangest space objects ever seen. A mysterious glowing green blob of gas is floating in space near a spiral galaxy, IC 2497. The object is so huge that it stretches more than 44,000 light-years to 136,000 light-years from the galaxy's core. It turns out that it's part of a 300,000 light-years long tidal tail that wraps around IC 2497. Our current understanding is that this part of the tail was illuminated by a high-energy beam created by matter falling into the galaxy's central black hole. Their unmistakable emerald hue is caused by ionized oxygen, which glows green. In our segment on the cosmos in the How Far Away Is It video book, we covered how, on the widest scale, the universe forms a web of galaxies surrounding great voids, and that the web filaments are galaxies grouped into superclusters. It has always been difficult for astronomers to determine where one supercluster ends and another begins. But now a team of astronomers have collected data on thousands of galaxies around us to understand their peculiar motion. You'll recall from our segment on local superclusters that the peculiar motion of an object is its motion less that part of its motion associated with the Hubble flow due to the expanding universe. They use this data to identify which galaxies are moving towards us, shown in blue, and which galaxies are moving away from us, shown in red. With this data, they were able to create a map of the paths galaxies are migrating along. These paths are called cosmic flows. Using this motion, they came up with a new way to map the distribution of matter in the universe. In our segment on the Virgo supercluster, we counted the Virgo galaxy cluster and a few hundred others as our local supercluster. But using this new technique, we see that the Virgo supercluster is part of a much larger structure that is 100 times larger and more massive. The astronomers who made this discovery have named the new supercluster Laniakea, Hawaiian for immeasurable heaven. Here is an illustration of Laniakea, along with Perseus Pisces, an adjacent supercluster. The boundary is where the supercluster objects are shearing apart, like the North American Great Divide separates water flowing to the Atlantic Ocean from water flowing to the Pacific Ocean. In this view, the red dot shows our Milky Way's location in Laniakea. Until the early part of the 20th century, it went without saying that the matter we see is most of the matter there is. That would be protons and neutrons, with accelerating electrons creating the light we see. But that came into question in the early 1930s, when Fritz Zwicky, a Swiss astronomer out of Caltech, studied the Coma Cluster, 321 million light-years away, with 1,000 galaxies spanning 25 million light-years in diameter. He looked at it in a number of ways, two of which are very revealing. In one, he used galaxy motion to calculate mass, and in the other, he used galaxy luminosity to calculate mass. His processes are not precise, but they do provide ballpark figures for the mass of the cluster. For motion, he had the cluster galaxies' radial velocities from the Doppler shift in the light we see. He then generalized them into their three-dimensional velocity dispersion statistical equivalent. This galaxy motion gives us the kinetic energy for the cluster. Zwicky used the well-understood virial theorem that has the kinetic energy of a system equal to 1/2 its gravitational potential energy. This allows us to solve for the mass of the cluster. This is the mass as measured by its gravitational effects. The second way he calculated the cluster's mass was to use the cluster's luminosity. You may recall from our discussion on the Hertzsprung-Russell diagram in our How Far Away Is It segment on distant stars that there is a relationship between a star's mass and its luminosity. We can use that relationship to estimate the mass of groups of stars by measuring their luminosity. We use the mass-to-light ratio of the Sun as the base for comparisons. For example, the Omega Centauri globular cluster has a mass-to-light ratio of 3.6. Zwicky measured the luminosity of the average galaxy in the Coma Cluster. Using a mass-to-light ratio of 3, he calculated its mass. When he multiplied the average times 1,000 galaxies in the cluster, he came out with a number that was over 100 times less than the mass calculated via the virial theorem based on gravity. In other words, the motion of the galaxies in the cluster indicated a mass that was over 100 times the mass from luminous matter. Zwicky concluded that either the laws of gravity as we know them, Newton's and Einstein's, did not work for volumes as large as the Coma Cluster, or the luminous matter is only a very small part of the total matter of the cluster. He called the rest of the matter dark matter, and suggested that gravitational lensing could help quantify this dark matter. But back in the 1930s, nobody believed him. Fast forward to the 1970s. Attention was focused on an anomaly associated with the velocity of stars orbiting spiral galaxies. Resolving the velocities of individual stars in distant galaxies is not feasible. But in spiral galaxies, where all the stars in the disk are rotating in the same direction, a good aggregate estimate is possible. With elliptical galaxies, the motion of stars around the center are chaotic, so we have no velocity data to use and therefore no anomalies to identify. To see how the velocities give us a measure of mass, we'll start with our solar system. Here's the rotation curve we get when we map the velocity of the planets orbiting the Sun. Because the Sun has 99% of all the matter in the system, the mass within any orbit will be relatively fixed at the Sun's mass. Therefore, the further away from the central mass we get, the weaker the gravitational pull and the slower the orbital velocity. This model is called Keplerian because it follows Kepler's laws for orbital motion. Now, a galaxy is much more complex than a solar system. The mass within increasing orbital volumes is not fixed like it is in the solar system. If you move out from the center of a galaxy, there is considerable mass added in addition to the mass of the central bulge. This is because of the large number of stars, dust, and gas in the galaxy's disk. For instance, it is estimated that the mass of the central bulge of the Milky Way is 20 billion solar masses. We saw in our segment on the Milky Way that the velocity of the Sun around the center of the galaxy is 200 kilometers per second, and its distance from the center is 26,000 light-years. So the mass of the galaxies interior to the Sun's orbit is approximately 74 billion solar masses, a good deal more than the bulge itself. But at the outer edges of the disk, the star density drops off dramatically. In the 1970s, everyone expected to see rotation curves that look like this. But in 1975, an American astronomer, Vera Rubin, published galaxy rotation curves for the Milky Way and a number of other galaxies that showed a remarkable result. Where the velocities were expected to fall off, they remained relatively constant. If our current theory of gravity holds up for galactic distances, then this curve tells us that our model of the Milky Way is missing something. In order for objects far from the center of the galaxy to be moving faster than predicted, there must be significant additional mass far from the galactic center, exerting gravitational pulls on those stars. In other words, dark matter. Here's Vera Rubin's measurements of the velocity curve for Andromeda. And here's the rotation curve for NGC 6503, the galaxy on the edge of the local void that we covered earlier. Using accurate and high-resolution emission lines from neutral hydrogen, astronomers modeled the mass distribution of this galaxy. They used the mass-to-light ratio in the visible disk, the galaxy's core radius, and the circular velocity of the halo. The study found the contribution to the rotation curve of three types of matter: gas, luminous matter, and dark matter. With this new understanding about the possibility and impact of dark matter, astronomers turned their attention back to galaxy clusters like the one studied by Zwicky in 1936. Back then, Zwicky suggested that gravitational lensing could be used to better understand dark matter. Our case-in-point galaxy is known as the Buldge cluster. The virial motion of its galaxies indicates that a collision has occurred. Two massive clusters have passed through each other millions of years ago, and member galaxies are now flying apart. If we zoom in a bit closer, we can see the telltale arcs of more distant galaxies lensed by the gravity of the Buldge cluster. Counting the lensed objects and the estimated amount of light bending involved for each one, a map of the area containing most of the mass of the cluster can be superimposed. We have used blue to indicate the locations where the vast majority of the matter must be located in order to get the observed lensing. Here we have the cluster's hot X-ray emitting gas detected by the Chandra X-ray Observatory. The two pink clumps contain most of the normal matter, sometimes referred to as baryonic matter, or matter made up of protons and neutrons. The bullet-shaped clump on the right is the hot gas from one cluster, which passed through the hot gas from the other cluster during the collision. When we superimpose the dark, baryonic, and visible components of the cluster's mass, we get the full picture. The galaxies and the dark matter have traveled a great deal further than the gas. This indicates that the galaxies and dark matter in the two colliding clusters did not interfere with each other. In other words, they passed through each other without slowing down. On the other hand, during the collision, the gas clouds were slowed by a drag force, similar to air resistance. This combination had the effect of separating the gas from the dark matter. This separation is considered to be direct evidence that dark matter exists. Measurements indicate that the galaxy clusters on average have 85% dark matter, 14% intergalactic gas, and only 1% stars. In 2014, a team of astronomers found a supernova in this galaxy cluster, over 5 billion light-years away. The supernova actually happened in a galaxy 4 billion light-years beyond that, making it 9 billion light-years away. The huge mass of the foreground galaxy and galaxy cluster bent the light from the distant supernova, creating 4 separate images of the same explosion. The images are arranged around an elliptical galaxy in a formation known as an Einstein cross. Following this discovery, astronomers modeled several possible gas and dark matter distributions in the galaxy cluster. Each model predicted that another image of this supernova will appear in the cluster, but they had different time estimates ranging from 2015 through 2025. In December 2015, it appeared. For the first time in history, the time and location of a supernova was accurately predicted. We actually saw the supernova happen. Instead of detecting a flash in the sky and turning telescopes to its location, we had the telescopes already focused on the correct area and recorded the event from beginning to end. This was powerful evidence for dark matter. We have seen two kinds of evidence for dark matter. One from galaxy rotation curves for dark matter around spiral galaxies, and the other from gravitational lensing for galaxy clusters. Both leave us with only two possibilities. Either our current theory of gravity just doesn't extend to galaxies and/or galaxy clusters, or most of the universe is made up of one or more unknown substances that interact with normal matter via gravity, but not much else. A tremendous amount of research is actively trying to find out what this stuff is. Here are some of the possibilities. Hydrogen, weakly interacting massive particles, WIMPs for short, neutrinos. Let's take a quick look at each of these. Here's a European Southern Observatory artist's representation of the distribution of dark matter around the Milky Way galaxy. You may recall from our How Far Away Is It segment on the Milky Way that in September of 2012, Chandra found evidence that the Milky Way galaxy is embedded with a large amount of hot gas in the halo. Counting this vast amount of gas, the mass of the halo is estimated to equal the mass of the stars in the galaxy. This could be the solution for star orbital speeds, and might be the answer for spiral galaxy dark matter. It could not be the answer for galaxy clusters, though. But then again, it doesn't have to be. Another possibility is the existence of a new set of extended standard model particles. There are a variety of theories that predict WIMPs. In late 2015, the Large Hadron Collider at CERN came back online after a 2-year upgrade. It can now reach 13 trillion electron volts, almost double the collision energy before the upgrade. At this level, it might be enough to produce a WIMP. Of course, the particle would not be detected because it wouldn't interact with any layer of the detector. However, it would carry away energy and momentum, so physicists could infer their existence from the amount of energy and momentum missing after a collision. You may remember from our How Small Is It elementary particle segment that this is exactly the same way Ellis and Worcester found the neutrino back in 1927. This brings us to the last possibility we'll cover. In our discussion on elementary particles, we found that the neutrino is a critical component in many nuclear reactions, and the detection of solar neutrinos and of neutrinos from supernova 1987A marked the beginning of neutrino astronomy. Over the life of the universe, countless numbers have been produced. There are over 1 billion times more abundant than the electrons, protons, and neutrons that make up stars, planets, and people. But are there enough of them to account for the dark matter in galaxy clusters? Neutrino astronomy is trying to discover the answer to this question. Today we have built amazing neutrino detectors, such as the Super Kamiokande in Japan, to better understand these fundamental but elusive particles. The Super Kamiokande is located 1,000 meters underground in a Japanese mine. It contains a lake holding 50,000 tons of ultra-pure water, surrounded by an inner detector with over 11,000 photomultiplier tubes that flash when struck by a photon created by a neutrino interaction with the water. The speed of light in water is slower than the speed of light in a vacuum. A neutrino interaction with the electrons or nuclei of water can produce a charged particle that moves faster than the speed of light in water. This creates a cone of light known as Cherenkov radiation. This is the optical equivalent of a sonic boom. The Cherenkov light is projected as a ring on the wall of the detector and recorded by the photomultipliers. With so much of the scientific community searching for an answer, we can expect to know if neutrinos, WIMPs, hydrogen, new gravitational theories, or something else can explain the movement of stars around galaxies and galaxies around clusters. Hopefully, there will be news to report on this topic in the 2016 update. Before listing all the sources I used to make this 2015 update, I'd like to point to 2 websites you might find interesting. One is Galaxy Zoo. It's a site where you help with over 1 million cataloged Hubble Galaxy images. Hanny's Voorwerp was found just this way, by Dutch schoolteacher Hanny van Arkel. The name is Dutch for Hanny's object. Amazing Space, Hubble's sister site, is launching a new look and feel. Amazing Space takes users on a journey of astronomical discovery through the nearby and distant cosmos, from the combined perspective of the Hubble Space Telescope and its successor, the James Webb Space Telescope. Take a look. And here are 2 articles worth reading. This is Fritz Zwicky's 1937 paper that first introduces the idea of dark matter. You'll find that it needs some amount of mathematics to understand. The second paper is a recent article by Vera Rubin that you'll find easier to read. And don't forget, every video segment on the How Far Away Is It YouTube channel, including this one, has a document with the text, pictures, links, and notes located on howfarawayisit.com/documents. Here are the links to the Hubble and other locations where I found the information contained in this 2015 update. These are the places you can go to learn more. Thank you for watching.